SEI Philly. Please take a moment to review this slide. As with any virtual meeting, whether it's Teams, Zoom, or WebEx, please remember to keep yourself on mute. Also note that this meeting will be recorded, and the link to the recorded event will be provided at a later date. During this presentation, if you have any questions or comments, please write them in the chat window, and the speakers will address them at the end of the presentation. I understand that many of us have meetings that bookend this 1 hour time slot, so we will try to honor this commitment. If we run a little over, please bear with us. So officially, welcome everyone to SEI Affiliate second meeting of the 2021 calendar year. I want to thank everyone for joining us today for a great presentation by Grant Fluffmeyer and Michael Urban. We have close to 100 people registered for this event. Again, that is an outstanding outcome. This shows the outreach these virtual meetings have, especially when we have a topic as interesting as this one. For those that are in attendance on this call, we will email a link to so you can download the PDH. Before I introduce Grant and Mike, I do want to recognize this year's board. They are myself, James Deeney, as the chair, James Greco as vice chair, Jack Cardinal as treasurer, Nikki Eno as secretary, Keith Merle as program director, Michael Urban as director of public relations, Colin Drager as deputy director of public relations, and Dan Cush as our past chair. So with that, I'd like to introduce today's speakers. Grant Fluffmeyer is a registered PE in Pennsylvania and a structural engineer at Gann Fleming's Valley Forge office. He has over 14 years of experience in design, analysis, and inspection of bridges and other transportation structures. He has participated in projects in PA, New Jersey, Ontario, Canada, and he obtained his bachelor's from Lehigh University. Welcome, Grant. Michael Urban is a registered PE in Pennsylvania and New Jersey, and a project manager at Gann Fleming's Valley Forge office. He has over 15 years of experience in design, construction, and inspection. Mike also has conducted extensive research on the evaluation, heat strengthening repair, and testing of severely damaged steel girders. Mike obtained his bachelor's from Drexel University and his master's from Lehigh University. Welcome, Mike. And Mike, hopefully we can persuade you to come speak to us again about the many heat straightening projects that you have completed over the years. Just a little plug there. So with that, gentlemen, the floor is yours.
Thank you, James. All right. So thank you, everyone, for showing up for this lunchtime webinar. I think the lunchtime is working for everyone. Just talking as a board member here. So today Grant and I are going to present to you the rehabilitation of Reading's historic Penn Street Bridge. This is finished almost a year ago, just about a year ago now. It was a great project to work on. So moving on, this presentation, we're going to give you an overview of the bridge itself, the purpose and the history behind, what made this bridge very important. One of the important things for this was the public outreach. We'll go over that. This isn't just a bridge project, the roadway portion of this, as well as the traffic, there was a lot of involvement. And then I'll let Grant explain the structures aspect of this project. Just want you to note in this slide, you can see in the upper right is the before picture. It was dark. They had that little retaining wall there that they added. Everything was pretty much falling apart, and then the below is just the completed project. So it's light. It's welcoming. Updated lighting. So it's, like I said, just to give you a little teaser of what's to come. So before I get into this, I just wanted to thank everybody that was involved in this. I think without the help of everybody that's on this slide, and even some that aren't on here, this wouldn't have been as successful of a project as it was. First and foremost, PennDOT District 5, from the management, design, construction, inspection, everybody there, it was great in making this project successful. For the design side on your right, Gannett Fleming was the prime, but just as important, were our subs: Susquehanna Civil, Specialty, CHRS, Liberty, and SoftDig. During the planning and preliminary design portion of this project, Berks County Planning Commission, City of Reading, West Reading, and the Reading Area Community College, which is also, you'll hear me say RAC. They were heavily involved in just, making this successful, as I said. And then onto construction, JD Ekman was the contractor and TRC was the construction inspector. I mean, top to bottom, everybody, they made this project, this bridge, their own, and it showed in the, when it was all done. So, thanks to everybody for making this as successful as it's been. So moving on into what the Penn Street Bridge is. Here's just a plan view of the entire structure. It's actually 14 spans. It spans the Schuylkill River, the Norfolk Southern Railroad, a Schuylkill River Trail, Front Street, the Reading Area Community College, and a utility access road. And this structure, it consists of 5 open spandrel spans. There's 9 closed spandrel spans with 8 on the east and the 1 right there you can see on the west. An approach pile supported chamber span, pile supported slab chamber span. And then when the 422 bypass was constructed later on, a ramp I structure was constructed. And you also have the ramp K, which ties into the span 1, as you see. So the purpose of this bridge was to rehabilitate the structurally deficient bridge to extend its useful life while preserving the character. This is listed on the National Register of Historic Places, so this was very important. And you can see in this photo right here, this postcard, it was a link between the Reading and West Reading. It was vibrant. People were out. This was the story to tell about Reading. This was their gateway coming in. It was built, like I said, in 1913. Then in 1948, after years of deterioration, they decided to place a gunite coating over the entire structure. They updated the roadway. As you can see, there was trolleys, so they converted it just to cars. They removed the outlooks on the piers and they added some drainage. And then I briefly mentioned in 1958, they constructed the West Shore bypass, which added the ramp I and ramp K. In the 70s, if you can see in the picture there, they had obelisks with gaslight lamps that they removed to put, at the time, modern light poles with the overhead lighting. And then finally in 2019, we had our rehab and restoration of this bridge. Come on. So as I mentioned, this is eligible for the National Register of Historic Places. In Berks County, it's the oldest bridge of its type. And it's on there for, like I said, the age, the type of construction, and this unique architecture. It is an open spandrel reinforced concrete arch bridge, those 5 main spans. Another important aspect is it has that reticulated pattern balustrade for a barrier. It has those pedestrian outlooks and all the detailing on on the fascia on the outside that you can see. And this bridge was part of the City Beautiful movement, and what that was, it was treating all the civic architecture, urban planning, everything else, and they were making it look nice. I mean, that's the purpose. That's why you have such a a gorgeous looking bridge, and that's what they were trying to do at the time. So obviously we want to bring that back. So in the early stages of design, public outreach was really important. There was consulting party meetings, public official meetings. We had a plans display where the community could come in and look, see what they were, see what we were doing. There was also adjacent projects, just upstream of here was the Buttonwood Bridge. They also had the Wyomissing project, ADA sidewalks, there was lighting, there was water line projects. So there was a lot of stuff going on. We had to make sure we were incorporating our work with everything else. And one of the funniest things about this was during design, there was actually a 100th birthday party for this bridge where people in the community, they came out, they had activities, they had a cake, and people actually sang happy birthday to this bridge. So just based on that, you could see how important this bridge was, to the community. And they took pride in this, and that, from that point on, we knew we had to take that into account. We had to make sure that we were incorporating that into our design, and we were being respectful of it. So we always wanted to stay on key to make sure that we were returning this bridge to its original condition. And then we also had to make sure that this was a bridge project. You have a lot of other things going on, but we wanted to maintain that focus, and everybody understood that from top to the bottom that this was a bridge project. However, we didn't want to preclude anything. There's also master plans. The RAC had master plans. I'll talk about bike lanes in a little bit. The different construction projects. We had to maintain that connectivity between West Reading and East Reading. And then once it's all done, ownership and maintenance, you have the lights, the sidewalks, everything. So it was always understanding who was involved, who was going to be involved, and making sure everybody was on board, everybody knew what was going on. And I think that was also key, is just always keeping people up to speed with how everything was going. And just before I skip over in the slide, when talking about public plans display, in the bottom right, you can see that's actually a rendering that we did to show the lighting to the public, and then obviously the background, that's the final product. So it came out really nice. So when talking about stakeholder and public engagement and everything else, we also, the Reading Eagle was the newspaper in the area, and we had a lot of talks with them. And this was actually in the middle here was they had a full page blow up of the bridge, explained everything that was going on, construction scheduling, detours. You can see in the upper left what the roadway was going to look like, what we were going to do. It was getting everybody involved. Everybody knew what was going on. Nobody had any, was in the dark with anything. And then in addition, they also sent out flyers. So all the residents of Reading, they wanted everybody to know that nothing was closing down. Reading was still opening. On the bottom right there, that was actually one of the billboards that they had. They just want to make sure everybody knew that Reading wasn't closing down. So getting into the project, here's just an aerial before. Penn Street had an ADT of over 22,000 car vehicles. You had the 422 interchange directly on the left, the west side, and you had the 2nd Street intersection directly on the east of the structure. So this structure was flanked by the intersection and the interchange right there. And it also crossed RAC. So the RAC is on both the north and south side of the bridge down over there on the east. So they had parking lots, they had pedestrian crossings underneath some of the spans. So there was a lot of stuff going on that Reading side. So then going into design, the existing cross section had originally 4 13-foot lanes, a 3-foot median, and 2 11-foot sidewalks. Now with those 13-foot lanes, it promoted a lot of speeding across. It's posted for 25, but with that long stretch of bridge and 13-foot lanes, you can just imagine how fast people were going across the bridge. So moving into the proposed section, one of the concerns between consulting parties and public outreach was that they wanted some protection on the sidewalks. So in the final condition, we reduced those lane widths to 11 feet. So you had 4 11-foot lanes. You had a 6-foot median separating the traffic a little bit more, a 5-foot shoulder to further keep the traffic away from the pedestrians, the crash-worthy curb barrier, and 2 7-foot sidewalks. That curb barrier allowed us to use a non-crash-worthy pedestrian barrier, which was the original design um, that was on the bridge, because we had to protect it, the pedestrians, and also have a crash-worthy barrier. And those 5-foot shoulders are wide enough that in the future they could become bike lanes, but at the time there was no facilities on either side of the bridge. However, again, as I mentioned before, we are not precluding those, and this way it's an easy to stripe, and all the inlets have the bicycle safety grates on them as well. So as I mentioned, there was a lot of traffic. This is the main route into Reading from 422. So a lot of traffic, a lot of people going in. So we had to do a study, determine how could we rehab this bridge and still maintain traffic. And it was decided early on that we needed to maintain 3 lanes. So that gave us, we had to knock 1 lane off. And to do that, we took out ramp K, which is the off ramp of 422 onto Penn Street going in. So that was the lane we were able to take out. So we had 2 detours actually. One was the further south prior to the bridge, and then just in case we had some concerns that if people not near the area missed that, we had another detour further north where they could come back around through West Reading and get back to the bridge. So it was, again, just making sure everybody could get across where they needed to, and just thinking ahead. And then throughout, there was some modification of the signal timings for this. So as I mentioned, once we took out that 1 lane, that gave us the ability to have for the stage construction. And there were 6 total construction stages, 3 of which were the 3 major stages. The 3 major stages, being the north side of the bridge, the south side, and then right down the middle. And a couple of the stages in between were just prep for those. The whole time we had to maintain the 3 lanes of traffic throughout construction, and we always had to have at least 1 sidewalk open to pedestrians throughout construction. So then moving on to structure, you can see that this bridge was in pretty bad shape. This is what you're looking at here is the shotcrete or the gunite coating that was placed on in the 50s. That was used to repair the deteriorated concrete. And in some locations that was up to 4 inches thick and as thin as maybe a half an inch, where there was, it ended up being like a skin coating. So it varied in thickness. And then, after time, that started to fail. Water was trapped, and you can see in the upper left, somewhere that gunite had failed, have come off, and then the original concrete had further deteriorated. Also note that on the pier right there, that is one of the outlooks, and when they closed that off, the outlook itself remained. It's just pedestrians couldn't get access to it, and all it did was collect dirt and debris, and weeds grew, and people just assumed that was it was built that way as a flower pot. So again, not the intention, and the idea was to bring that back. There was the water line on there, and just lots of spalling, cracking, and everything. Then moving on to the closed spandrel spans, again, same thing. You can see the cracking, the deterioration, the leaking. You can see by all the effervescence, there was water behind there. This is actually in the center is the picture of that chamber span. It's pile supported slab with the walls. So it was an inaccessible span, and then I believe it's like 2003, they added that access door to finally get access to that chamber span so they could inspect it. And then in the back of that picture, you can kind of see that retaining wall that was put in, but just a lot of cracking of the gunite and everything. And then on top, you can see the barrier there. cracking, spalling, typical, what you would think of a 100-year-old concrete bridge. There's some locations where the barrier was actually leaning and had to be held up. The sidewalk, patching, cracking, heaving, same thing. The asphalt roadway had cracks and it wasn't level. So a lot of stuff that needed to be be rehabbed. And then, as I mentioned, you can see our flowers, our weeds growing in the flower box right there. And then the ramp I structure on the left, it was a 2-span monolithic T-beam structure that they added for ramp I, and the picture on your right is just a top view of that. And then, as you can see, the asbestos covered Verizon fiber optic lines that could not be disrupted during construction, going right through the hammerhead pier, and then it would go into the abutment. So all those then went up into span 2 onto Penn Street and was in the northern sidewalk there. So Grant will talk about that, everything we had to deal with those Verizon lines. And then in the bottom picture there, that's ramp K. And if you look closely at that metal railing, you can see how the ramp K actually settled because they put a retaining wall to close off the span 1, and the soil behind it settled, and you can see how the barrier settled as well. So a lot of stuff going on for this. So at this point, I'm going to hand it over to Grant, and he'll talk about the actual rehabilitation.
Okay, Mike. I'm going to try to get my slides up here. If you can let me know if you can see them.
Yes, sir.
Awesome. Okay, thank you, Mike. I'm just going to talk about the general approach and the strategy to the rehabilitation of the Penn Street Bridge, and then move on to some interesting aspects of the design and go through the construction of the rehab. Early in the project, we did an in-depth, hands-on inspection of the structure to determine the extent of the rehabilitation and then develop a strategy from that. Since the bridge was historic, our goal was to try to save as much of the original structure as possible. But during our inspection, we found that there were a lot of elements of the bridge that had advanced deterioration and would have to be replaced. And those that happened to be pretty much the whole top side of the bridge had to be removed and replaced, which included the deck, the floor beams, the jack arches, the railings, the sidewalks, and the existing lighting. The lower portions of the bridge, the arch ribs in the open spandrel arch spans, the spandrel columns, they could be salvaged, and so could the arch barrels and the closed spandrel spans and the spandrel walls and the piers. They had enough capacity and all that stuff. They pretty much just had to be rehabilitated with concrete repairs. And for the replaced portions of the bridge, we tried to be sensitive to the characteristics of the original bridge. We used the original design drawings to recreate a lot of the architectural details and match it so the rehabbed bridge had the same appearance and aesthetics as the original. So one of the unique features of the Penn Street Bridge is that in the open spandrel spans, the deck slab had no expansion joints. This was an unusual feature for this type of bridge. No other bridges in the area had this this no expansion joint condition. And when we did our in-depth inspection of the bridge, we found that there was no evidence of thermal damage or any damage to the deck or other related elements due to thermal expansion and contraction. So we determined that we wanted the new deck, the proposed deck, to also not have any expansion joints to match the existing condition, but we wanted to design it to modern codes and account for thermal expansion and contraction and all the forces that go along with that. Our analysis determined that tensile forces in the deck were the critical forces. Pretty much when the bridge cooled down and contracted, the piers were rigid and the arch was pretty rigid. There would be some elastic shortening of the arch with the cooling and contraction, but the arches were pretty stout, so that was pretty minimal and sort of negligible. So pretty much what would happen is as the deck tried to contract, the piers and the arches would hold it in place, and large tensile stresses would form in the deck due to the contraction of the bridge. And this was relatively easy to design for when it came to the tension and the moment design. We had pretty heavy longitudinal reinforcement in the deck. So we determined that the stress due to thermal loads in that reinforcement would be approximately 5 KSI. And so we approached the moment design by reducing the allowable stress in the longitudinal deck reinforcement by 5 KSI and coming up with a reserve capacity that then we used to design the dead load and live load in the deck. The tricky part about the deck design was the shear capacity. The ACI 318 code has a provision that says when the tensile stress in a concrete member increases to 500 PSI, the shear capacity of that concrete member linearly decreases to 0, pretty much no capacity at all. And a lot of the stresses we were finding, the tensile stresses in this deck were over 500 PSI. So theoretically, according to the ACI code, the deck had no shear capacity. Now, looking at the existing deck, we didn't think that was true. We thought that was the ACI code was a little conservative. So we actually did a more, using modified compression field theory, and found that the longitude, because the deck was heavily reinforced longitudinally and the reinforcement was evenly distributed through the deck, that the deck actually had a lot of shear capacity, and the longitudinal reinforcement contributed to that. And we found that we really didn't have to add any additional reinforcement to account for the shear in the deck, even though we did add Z-bars at the floor beam supports just as like an extra measure to account for the shear. So the open spandrel spans consisted of 3 arch ribs. There were 2 exterior arch ribs that were 10 feet wide and 1 interior arch rib that was 16 feet wide. And to keep the lanes on the bridge, what we did is we shifted traffic during construction to 2 of the arch ribs. And we had to do analysis of the arch ribs to make sure that they could handle the loads in this temporary condition, which they could. Some of the floor beams, which exhibited some pretty severe deterioration, had to be temporarily supported during these stages in locations where the deterioration affected the capacity significantly. But once the traffic was shifted to 2 arches, we could proceed with removal of the deck, sidewalks, and barriers and the top side of the bridge, as you can see here. We also removed the floor beams, but we salvaged the bottom reinforcement in the floor beams. The reason we did that is that those bars were embedded in the existing arch ribs and spandrel columns, and keeping them there, we could tie the new floor beam reinforcement to those existing bars and have a good positive connection between the existing structure and the new floor beams. We also removed the jack arch and then select spandrel columns. The spandrel columns that we removed were selected in the field. When the gunite was removed, we could really assess the concrete underneath, and we found that there was a bunch of spandrel columns that needed to be replaced fully, and we had a detail on the plans to do that. So once the top side of the bridge was removed, as you can see here, we could perform concrete repairs on the arch ribs and the piers. The picture here on the left shows a type 2 repair to the arch rib. This is actually the north rib in span 6, which was the most severely deteriorated of all those arch ribs. And as you can see here in the picture, you can see the surface of the new concrete and then the surface of the old concrete. We actually, when the contractor was out there removing concrete, they were actually digging pretty deep into this rib. And we actually had to stop removal and come up with a strategy and sequence to actually do the repairs on this arch rib without destabilizing it at all. So we came up with a strategy and repaired that. And the picture on the right, you'll notice that there's those big steel towers. That is actually a temporary utility bridge. As Mike mentioned earlier, there were fiber optic communication conduits in the existing sidewalk that could not be disconnected during construction. They had to be maintained. And since we were taking the top side of the bridge off, we had to move them. They had to be moved to this temporary utility bridge while the top was constructed. And once the new deck was on, we could move them back into new conduits and embedded in the new sidewalk. So once the concrete repairs were being done, we could reconstruct the spandrel columns and the jack arches. As you can see here, one thing we added back was the scoring on the outside face of the arch ribs. This was a detail that was on the original arch ribs, but that a lot of these score lines were deteriorated away or covered in shotcrete. So we added them back onto the rehabilitated arch ribs. And then we constructed the new floor beams. Here are the rebar cages for the new floor beams. You can see what we did is we tied the existing bars that were projecting from those spandrel columns and arch ribs, tied them to the new rebar cages, and created a good positive connection between the existing and the new floor beams. Then we cast the floor beams in place, maintaining a lot of the original, like the chamfers at the top of the floor beams. Those were matching the original details from the original bridge. And the floor beams were made composite with the deck slab. And since the bridge was historic, we had to use removable forms on the deck slab, as you can see here. So here are the utilities in the sidewalk. They were moved from that temporary bridge onto the new sidewalk, put in new split conduits, but there were these large splices in the conduits in the middle of the bridge, which we had to accommodate. And the way we did that is we designed one of the arch or the jack arches to have this, what we called a utility splice vault. It was pretty much a large pocket in the jack arch that we could house these splices in. And then after the deck or after the sidewalk was cast, we have access panels now there so people can get in and work on these splices if they need. Here is the outlooks. As Mike said, these were closed off in a previous rehabilitation. We reconstructed them. And here you can see the conduits. Those are conduits for the bridge lighting on the top side and below the bridge that ran through the pedestrian barriers. Moving on to the closed spandrel spans. The first step in the rehabilitation of the closed spandrel spans was to remove the existing asphalt roadway and concrete slab, exposing the original dirt fill. And then we drove sheeting through the fill to the top of the existing arch barrels, matching the profile of those arch barrels. And once that sheeting was installed, they could remove the fill. Once they got down to the arch barrels, they anchored this sheeting to the top of the arch rib or the arch barrel, and it created good temporary support for the fill on the other side. And traffic actually was pretty close. This is the barrier up here, right adjacent to that sheeting. Once the fill was removed, we could clean and repair the top of the arch, and new weep holes were drilled at the base of the arch. Along with the weep holes, a sloped concrete pad was constructed to promote drainage from the base of the arch to those weep holes. And then once that was all done, waterproofing was applied to the top of the arch and to the inside faces of the spandrel walls. And to fill in on top of the arch, we used cellular concrete fill. The reason we used this is because it had a number of advantageous properties. First off, it was lightweight. This helped with balancing the new and the existing and proposed loads. The proposed loads were slightly higher, so having the lightweight fill helped balance everything out, so there was no overstressing of the existing arch or additional weight applied to the foundations. Another advantageous property of cellular fill is that it's permeable. So any water that leaked through into this fill would drain directly through to those weep holes that we drilled at the bottom of the arch barrels. This way, it avoided any water pooling above the arch. And the third property that was very advantageous was that it was self-supporting. And this came into play with the staging. When traffic was moved back onto these portions of the bridge, the cellular fill could hold up the traffic loads without requiring any additional temporary excavation support. It could self-support the traffic loads actually pretty close to the edge. So once the fill was put in, full width concrete moment slabs were constructed and the sidewalks were constructed on top of the closed spandrel arches. So to recreate the balusters, a combination precast cast in place system was used. We used precast panels because they had for a few reasons actually. One, it reduced the construction duration. These could be cast on site while other work was going on, so they'd be ready there to go once the barriers were ready to be constructed. And this, one of the other reasons is that it ensured a quality product. What the contractor actually did was he closed off one of the closed spandrel spans with plastic and created sort of a little fabrication shop below that arch span where they had these reusable forms that they formed these panels with. And here you can see the panels on the floor. They have they tied the rebar in there, and then they poured the concrete, and these are what the completed panels look like. They're concrete finish and very accurate with the detailing. And they could form these, it's almost like a production line. They could store these on site. So when the barrier was ready to be constructed, these are ready to go. So here are the panels in place. The panels had these nice little legs on them, so they could be placed on the sidewalk, and then they only had to be braced laterally. And they had bars projecting from them, which then tied into the cast in place bars, which are tied for the railings and the posts and the curbs. So once all those bars were tied, the cast in place portions were cast around those panels, and everything was locked together. Here you can see one of the posts. All the details match the original posts, and same with the rails and the curbs. So here's the finished product. It actually turned out really well. They really matched the existing or the original barriers. Now these barriers weren't crash worthy, as Mike mentioned. We had a 10M barrier at the curb line of the sidewalk. So these barriers were designed for pedestrian loads and wind loads, not crash loads. So span 1, as Mike mentioned, was the closed spandrel span at the west end of the bridge that was enclosed with the construction of the 422 bypass. When the ramps were built, they put retaining walls on either side of the closed spandrel span, and the only access really to the span was through these openings in the pier. And this was a problem for inspection. It was a confined space, and we really wanted to get rid of this. It wasn't really a necessary span anymore, but since it was historic, we decided to fill in the span with cellular concrete. What we did is we closed off those openings and then pumped cellular concrete below and above the arch barrel. So the historic arch barrel is still there, it's just filled in. And we had a similar approach to the chamber span. This again was a confined space, so it wasn't, easily accessible for inspection. We filled this in with cellular concrete too. We reused the sidewalls, and one of the interesting things, you can't see it in this picture, but there was actually cobblestones from the original road that came down from the city to the river here. So we wanted to preserve those historic cobblestones. So a layer of geotextile was put over them, and then the cellular concrete fill was put in on top. And once the cellular concrete fill was put in, the floor beams were removed. We didn't want any hard spots. You have floor beam cellular concrete. We didn't want any cracking of the roadway above, so those floor beams were removed. The whole thing was filled in. So onto the ramp I structure. As Mike mentioned, this was a 2-span concrete T-beam structure that was built in the 50s to accommodate an off-ramp from Penn Street onto 422 westbound. And the existing superstructure did not rate for current legal loads. So we had to replace the superstructure. The substructure, however, could be salvaged with minor modifications. And one of the things we had to work around, as Mike mentioned, were these conduits that ran underneath ramp I, through the pier and through the abutment. These had to be maintained during construction, these are the same conduits that came in on that utility bridge on the main span. And to make it more difficult, the conduits were asbestos containing. So they had to be shielded during construction so those asbestos conduits wouldn't be damaged. So here's the existing superstructure removed. We made some minor modifications to the beam seats to take the new superstructure. And the only pier that only substructure unit that really required any strengthening was the footing of the column, which was at the east end of ramp I. The new loads from the new superstructure overstressed some of the existing piles. So what we did is we drilled holes through the existing footing and installed micro piles, which were then cast into the existing footing, providing additional capacity to resist the new loads. So ramp by was a quirky little structure. As you can see from this framing plan here, it was triangular in shape. It only had one abutment. The beams were supported on one abutment on one side. There was a hammerhead pier that came off perpendicular from Penn Street, which supported two of the girders. And then there was a header beam that ran parallel to Penn Street that supported the girders along that face. It had severe skews, varying skews, required a substringer that tied into the fascia beam to at the east end of the bridge. And one of the interesting things, we used steel girders here to minimize the weight, but it wasn't strength that determined the size of the steel girders. It was actually the geometry. AASHTO and PennDOT have a provision that says that the steel beams cannot be, they have to be greater in depth than the overhang is in width. And based on this geometry, we needed 36-inch deep beams to meet that criteria. And even with the lightest W36, the capacity was still far greater than what was required for ramp by. And it was actually advantageous because with these beefier sections, there was actually less deflection. So differential deflections between the girders weren't as severe. They were actually minimized based on that. And along the, as I mentioned, there was a header beam along that paralleled the arch bridge. This was built in two stages. The header beam, the new header beam would sit on the existing substructure unit. So the depth of the header beam was limited. We couldn't make it too deep. Plus there was a utility access road that ran below ramp by, and we had to maintain vertical clearances there. So the header beam had to be constructed with shored construction. Pretty much the bottom portion of the header beam was cast. The steel girders were placed on that. And then the deck was poured. All the dead load was deflected out of the girders. And then the top portion of the header beam was cast. And this sequencing avoided locking in on any unnecessary dead load stresses in that header beam. Here's another picture from the top side of ramp by during construction with the shielded utilities. And I believe the header beam is being cast there in all that formwork. And here are the steel girders in place. It's hard to see, but you can maybe see the steel girders sitting on top of that bottom portion of the header beam. The ends of these girders were then cast into the header beam. And here's ramp by in its final condition in the top side. The deck, the sidewalks, and the barriers were poured. And one thing to note is the barrier here. We could not put a crash-worthy barrier at the sidewalk on ramp by. So what we actually did is we had a 2-foot thick crash-worthy barrier on the outside face, but we used form liners on that barrier to match the aesthetics of the pedestrian railing on the main line. And one thing we did add, we have a strip seal along the interface between the Penn Street Bridge and ramp by, and this was to create some separation between the two structures. So here are some stats for the project. The cost, it was budgeted at $42.5 million, and it actually came in at $43.2 million, which was 2% over budget. Pretty good for a project of this size. The schedule, the notice to proceed, was in November of 2016, and the estimated completion date was going to be December of 2019, but the contractor was able to finish up, and the actual completion date was in November of 2019. And here are some statistics for the different materials that were used on the job. There's approximately 5,800 cubic yards of concrete poured, almost 800,000 pounds of rebar, 6,500 mechanical splices, and 9,280 cubic yards of cellular concrete. We had a lot of type 1 and type 2 repairs on the existing concrete, 11,000 square feet of type 1 and close to 19,000 cubic yards of type 2 repairs. With all those concrete repairs, we realized that there was going to be a difference in texture and color between the existing concrete and the new patched areas. So what we actually did is we actually coated the entire structure in a 2-part coating that provides sort of uniform texture and color to the final product. And that turned out to be 17,000 square yards of coating. And we did provide a causeway below the bridge. Access from the top side was limited due to the staging and the required 3 lanes. So there was a large causeway built below the bridge to allow the contractor to do a lot of work from down below. And that was 9,000 cubic yards of R6 rock used in that causeway. So that concludes our presentation, and I guess we'll open it up. Thanks everyone for listening. I guess we'll open it up for questions now.
If anybody has a question, if you just want to put it in the chat window, I'll leave it open for a minute. Jim left, so I guess no questions. Oh, here we go. Question came in, how was the coordination with the city of Reading? So the coordination with the city was great. I mean, I think, like I said, everybody was involved from the beginning. We actually had the consulting party meetings. We had other meetings within the city. Same thing, you know, West Reading, don't forget them as well. They were on the other side, but I think they were just as involved even during construction. We always had, during our project control meetings, we always had a rep from West Reading and Reading there to just go over the project. And honestly, it's just the constant communication throughout the project is what made this successful. So everybody always knew what was going on, so there was no, you know, surprises, no hiccups. I think, you know, I think that was, I couldn't say that there was anything wrong with the coordination. Was the RAC pleased? Yes, the RAC was. Again, they were always at our public coordination meetings. You know, when Grant and I went out to do the inspection for, you know, in the beginning during PE and final, you know, we always let them know. They were very helpful. You know, when we did the lighting, they were always out, you know, to help us with everything, you know, just get access to panels. And it was just the same thing. They said, just keep us posted. We don't care what you do, just keep us posted. If you're going to come out, just let us know. And then during construction, you know, we worked with them. There was a couple things, you know, fix this, but, you know, the contractor was very responsive. PennDOT was very responsive to that. So, you know, they did have, you know, we closed off, you know, connection between their campus, you know, the parking lots, but, you know, whenever we did those, we tried to do it during summer. And we always try to maintain that access from both sides. There was always one of the spans open, you know, during that. So it was good. The next question was, with the bridge being historic, what stipulations were required by PHMC? So for this, we had, we pretty much went in knowing that we were going to bring it back to its original condition. You know, we had to address the concrete curb and the concrete curb and the new cross section. You know, with the obelisks in this picture, you can see there, you know, on the east end, you know, originally those were at every light pole. Now we couldn't do that. So we had to use more modern type lighting, but we went back to period lighting, and we were able to put the obelisk at the end, and there is actual, you can't see it, but there is up lighting to light those obelisks up at night for different LEDs. So we went in knowing that we were going to do this. So I don't think there was a lot of, you know, back and forth. You know, I think they were pretty happy with the way we approached the project. Did you consider non-permeable fill for the arches to prevent propagation of water through the arch fill and deterioration of arch barrel inside and out for the future? We did not. We just decided to go straight into permeable. We knew water was going to get in there. There's no way you were going to stop it. We just went right in, allowed that water to get through, and just be done with it, knowing that it was going to get in. Was there planning to include the future 422 expansion? There was not. We were aware. We knew. We had ideas what to do with the with the interchange, but again, we focused on making this a bridge project. We knew if we started going beyond that, you know, you have scope creep and everything. We focused on that, you know, this being a bridge project. So yeah, no, we did not go into addressing the 422 expansion. Next question, what type of foundations are supporting the various segments? Did you confirm bearing or maintain loads similar to current? So these are all, the bedrock's pretty close. So these are all spread footings, except at the west end span, the span one abutment had some concrete piles, and I believe the chamber span had concrete piles as well. So the goal was to just go, let's maintain the weight and not have to, you know, look into having to address the substructures, and you know, the open spandrel span piers were really massive. So
And the ramp I structure had concrete piles, which
correct.
The dead loads actually decreased on the hammerhead pier and the abutment because of the new superstructure. It was just that one column pier that saw increases in loads, and that's why we used the micro piles to retrofit that footing.
Next question, I guess comment, just great presentation. Thank you for attention to the historic significance. Yeah, I think, you know, going in with that, I think it made it easier. You know, you didn't get a lot of pushback from the community or, you know, anybody else. You know, if we were respectful from it from the get-go, and obviously it paid off. Can you speak to the input from members of the community? What were their concerns besides accessibility and bridge closure? Safety. Like I said, the RAC has a lot of people walking across this bridge, and you know, regardless of it being a crash-worthy barrier at the curb, I mean, they wanted a barrier. They said, we want to protect our students. I think that was I think that was their main concern. You know, was just safety of the pedestrian. So, you know, we complied. We have the 5-foot shoulder that we put in there. We had the crash-worthy barrier. I think that was one of their concerns about that. The other one was the community. You know, in the beginning, they were all concerned that Reading was going to be shut down. We're closing it. Nobody's going to go into the city, and they expressed that. But with you know, you saw the billboards and everybody, the Berks Planning Commission, you know, they made everybody aware Reading's not closed down. And at the end of the project, you know, one of the local places there, the Peanut Bar, you know, I met the owner in the beginning of the project, and you know, at the end of the project, we went back out there just to celebrate. And I asked him, I was like, you know, how'd it go? You know, and he was like, you know what, it was great. Everybody communicated. We didn't really see any drop off. You know, you guys did a great job. So again, it's just communication and keeping everybody involved. Next one was, what constitutes confined space under the bridge? It's essentially the depth, access, and air. I believe that's it, Grant. It's how far in you go, airflow. You know, you go in, you have a monitor, but before that, you have a safety plan. You know, there's things that go into it. So definitely that chamber span and span one.
Yeah, chamber span. We had to wear the air monitors when we went in, and someone had to be outside at all times to make sure that everything was safe. And so
the next question here is ECMS number 10740, I believe is what it was.
That sounds right.
Yeah, 1010740. Yes. What was the difference in the type 1 and the type 2? Type 1 was just more a surface. It didn't go to the rebar. The type 2 actually went past the rebar. And in Grant's stats that he showed up, you could see the type 1 was in square footage since it's not that deep. But I think it was during bid phase, we ended up switching over to a volume, a cubic foot, because the depth of the repair varied throughout. So when we did our hands-on inspection, we had that depth. You know, we were able to estimate that. So we converted that over to a cubic foot. So I I think that was easier for the contractor to bid on. Last one, was there ever a mayfly issue due to the lighting, and was mitigation added? Mayfly, I'm not sure. Grant?
I don't know.
I don't know, Mark, if you want to unmute. Yeah, I'm not 100% sure with the mayfly. I don't. Nothing was mitigated due to a mayfly issue, so I guess it was not an issue.
Yeah, several river crossings, especially with lighting. I know Danville had an issue when we did that project where the PennDOT maintenance would literally come out and plow the road because of the mayflies. I know that it's been mentioned on several other river crossings, and I didn't know if it was an issue here or not.
Yeah, we didn't have we didn't have anything, no. I think that's it for questions, and I think we just hit about our time. So, James?
Yes, Mike, thanks a lot. Everybody, just give me 2 minutes real quick. Thank you, Grant and Mike, for a great presentation. That was very informative. To show our appreciation, the SEI board would like to present you virtually, of course, certificate of appreciation and these pint glasses as you see in front of you with the SEI logo. We'll find a way to get these to you hopefully in the near future. Just a few announcements while we still have a little bit of time. Our next meeting will be in early December. We're still working on the date and topic, so please keep your eyes open for any emails from ASCE or SEI. Again, this will be another lunchtime virtual event. And one more thing, I want to take a moment to call upon future presenters. You know, one of the objectives of SEI Philadelphia is to advance the science, practice, and profession of structural engineering. This is done in part by providing these types of presentations to members who are interested in the topic of structural engineering. So if anyone in the audience would like to present or knows somebody who would like to present, please contact SCI Philly. Given that we will be doing these virtual meetings for the foreseeable future, we were able to reach out to a larger audience. And we also give out great gifts, as you can see by these pint glasses. That's all I have. I want to thank Grant and Mike again for a great presentation, but I also want to thank everyone who attended today. The portion of today's proceeds will go to SEI Scholarship Fund and our College Day Fund. So thank you for helping us promote the practice of engineering and structural engineering amongst the students. Again, that's all I have. Hope to see you guys or everyone in December. Thank you. Thank you, Mike and Grant.